to get going. Welcome everybody, and thank you for attending our first NISAR ISRO Community Workshop. This workshop will have a focus on performing an InSAR time series with MintPy, the Miami InSAR time series software. We will be demonstrating how to search ASF data and leverage various services, including on-demand processing, and we will perform the workflow in Open Science Lab, in OpenSAR Lab, which is ASF's public Jupyter Hub. I would like to extend our deep gratitude to Dr. Y.S. Rao from the Center of Studies and Resources Engineering at the Indian Institute of Technology for his work in organizing this workshop and communicating with all of our participants in India and helping to set up a good time that worked for everybody. So hopefully everybody in India is still awake, and hopefully everybody in the United States is has had their morning coffee. So we're all ready to get going here. And so before I dive into a little bit more of an intro into what we'll be covering, I'd like to introduce myself and my colleagues who I'm here with today. So I'm Alex Lewandowski. I'm a software engineer on the Open Science Lab team at the Alaska Satellite Facility, and today I'm here with Heidi Kristenson and Dr. Forrest Williams. So they can introduce themselves.
Hello, everyone. I'm Heidi Kristenson. I'm a GIS specialist at ASF, and I'm excited to present some basic SAR information.
And hello, everybody. My name is Dr. Forrest Williams, but you can just call me Forrest. I have a PhD in geosciences, where I focused on using SAR and InSAR analyses to track the movement of landslides across New Zealand. And I'm now at ASF working as a research software engineer, which means I'm one part scientist, one part software engineer. So I know a little bit about a lot, but not much about a particular thing.
Great, and now I'll just share our slide deck here. Okay, are you guys seeing the slides? Okay. All right, so these slides that we'll be working through today are available for reference. You can grab that QR code, and we can also post the link in the chat, which I'll do right now. So I'm just dropping this link into chat. And today, and so the course is broken up into 2 days. And so today we'll start off with this introduction to the workshop itself, and then Heidi will take over for an introduction into SAR, and then I will demonstrate our web app for data search and discovery, and also the interface for ordering on-demand products from HyP, which is Vertex. Then we'll have a short break, and then Forrest will pick up with an intro to InSAR and an additional dive into HyP on-demand processing. Then we'll have a short wrap-up. There is an optional homework assignment if you would like to process your own data in MintPy tomorrow. Then over the course of the day today, you'll learn how to put together an SBAS stack, and you can put together your own stack to run through the notebooks synchronously with the workshop tomorrow. I would also like to note that the workshop is being recorded, and these recordings will be hosted on ASF's YouTube page. And so if you're unable to work through synchronously with the workshop, you can always follow along after the fact. And we are also always here to answer questions that may pop up. There is a QA activated on the Zoom, and we will try to get to any questions that come through that QA, but we'll also go through afterwards. So if your question doesn't get answered, please rest assured that we will look at that after the fact and get back in touch with you. Then on the second day, Forrest will pick up again with an intro to the InSAR time series notebook that we'll be using. He'll walk through and explain what each step is, what's happening in each step. Then we'll have an opportunity for a QA, and then we'll end up running the actual notebook. We've got over an hour, about an hour and a quarter to run through that notebook, and so that's when if you've developed your own SBAS stack, you'll have an opportunity to run that yourself and potentially encounter problems, and we'll be on hand to work through that notebook with you and help steer you clear of any possible problems that could pop up. And then finally, we'll have a little wrap up, and that will conclude the workshop. So here are some helpful resources. So we did send out a sort of a preparatory slideshow to show you how to sign up for an Open Science Lab account. Sign up if you don't already have one. Sign up for an Earth Data Login account and accept the terms of use on the ASF data sets. There was also a section on getting a Copernicus Climate Data Store account and setting up your API keys and also installing the required software environment in OpenSAR Lab. And so if you haven't done that yet and wish to follow along during the workshop synchronously, I'd recommend that you grab these slides and work through that process, and just let us know if you have any trouble with any of those steps. And if you're working through asynchronously, then this is something that you can do after the fact as well. I've also linked ASF Data Search, which is the web app that we'll be demonstrating for finding the data and creating an SBAS stack and ordering those interferograms from HyP. There's a link to the HyP documentation, a link to Open Science Lab, and if you have any questions, this is our user support email. You can feel free to reach out to us, and our user support team will make sure that that your questions get to the right person. And then there's also a link to the ASF YouTube channel here. Of course, these recordings won't be posted until the workshop is completed, probably not for several days after the workshop is completed. All right, and with that, I will stop sharing so Heidi can pick up.
Thanks, Alex. Are you seeing my slides okay?
Yes.
Perfect. All right. Welcome, everyone. I don't have time to do a deep dive in 30 minutes, but I do want to touch on some of the key characteristics of synthetic aperture radar. We do include at the end of this slideshow a number of resources that include workshops and webinars that are available if you're interested in doing a bit of a deeper dive on your own. And one quick question, can you see my big yellow mouse?
I can see a small mouse.
Yes.
You don't see the yellow mouse?
It's not yellow, it's just an arrow, but I can see it.
Oh, okay. I had made it big, but I guess that doesn't translate to Zoom. So, all right, well, we'll go with that then. So synthetic aperture radar makes use of the microwave range of the electromagnetic spectrum, and this ranges from about 1 centimeter to about 1 meter in wavelength. This takes advantage of a window where the atmosphere is quite clear, so the signals can penetrate through clouds and smoke, which makes SAR an excellent resource for monitoring surface processes during events like a hurricane or wildfire where there's smoke or cloud that prevents optical imagery from actually being able to image the surface. So that's a huge advantage of SAR. And in addition, SAR does not make use of sunlight. It's an active imaging system. So it is sending down a very controlled pulse of a signal, and then only the return of that controlled signal is actually measured. So you don't need any sunlight to illuminate the scene. It is basically self-illuminating. So that means between those two things that you can always acquire an image when you are looking down from space, regardless of the cloud conditions, any smoke that's present, or also regardless of the time of night or day. So these capabilities make it possible to have these regularly sampled high resolution and weather independent Earth observation data from space, which really lends SAR well to monitoring a time series approach, or looking at consistent processes, looking at processes consistently through time. It does tell you different things than optical imagery does, so it can't be used as a direct replacement. But for areas that are especially prone to cloud cover, it can be a very valuable tool for monitoring surface processes. Synthetic aperture radar uses a side-looking geometry to collect the imagery. So it's always looking down at an angle from the sensor to the surface of the Earth. The angle will be a little bit different in the near range and the far range. And this allows the sensor to actually use the time that it takes for the signal to come back to determine how to map those returns to where it would be coming from on the Earth's surface. So this is really different from most optical imagery, which you tend to be looking straight down. It's a nadir approach where you're looking right down at the Earth. And if we do that with SAR, because the mapping of the location is happening based on the time that it takes for the signal to return, you could be getting returns coming back from both the left and the right side at the same time, and it would be ambiguous which direction that was coming from, so you wouldn't be able to resolve that image. So it's necessary to use the side-looking geometry, because then you know that there's only one place on the Earth that it can be coming from. It's necessary for acquiring these images, but it does mean that there are certain distortions that are inherent to SAR data sets. And it's important to be aware of those and potentially correct for them before using the data for analysis. And I'll be going into that in a bit more detail later. So imaging from space using radar is complicated by the fact that the farther away you get with a radar sensor, the lower the resolution is of the image that you're acquiring. So for a C-band radar that's mounted on a satellite, if you had a 10-meter antenna, you'd only be able to get about a 5-kilometer resolution, which does not provide very much detail. You could get around that by having a much longer antenna. So if you had a 5-kilometer long antenna, you could get 10-meter resolution, but it's completely impractical to fly a 5-kilometer long antenna on a spacecraft. So to get around that, synthetic aperture radar uses the motion of the sensor as a proxy for a longer antenna. So you're collecting images, the sensor is flying along and collecting a series of images, each with a very wide footprint. You've got that very low resolution. But as it collects data, there are objects on the Earth's surface that will be present in multiple of these adjacent acquisitions. And we can use those multiple acquisitions to focus the image into a high resolution version that synthesizes having a much longer antenna, even though it's actually just a series of individual images along the flight direction of the sensor. So this gets around that problem of needing a long antenna. We essentially synthetically create a much longer antenna so that we can collect high resolution data even from very far out in space. There are two different components of the SAR data set, the amplitude and the phase. The amplitude is how much of the signal that's sent out actually returns to the sensor to be measured. That's also called backscatter or intensity. The amount of backscatter will be impacted by both the sensor properties, but also the physical and dielectric characteristics of the scatterers on the Earth's surface. For most of this introduction, I'll be focusing on the amplitude part of the data set and the actual imagery, whereas Forrest will be focusing more on the phase. And the phase is the location of the signal along its wave cycle when it returns to the sensor. This is the part of the data set that allows the amplitude to be mapped to that place on Earth. As I mentioned, it's all about the timing that it takes for the signal to come back to the sensor. So the phase is what allows us to map the amplitude to the Earth, but it also has a lot of useful information on its own. That phase is a proxy for distance, and this is the basis of SAR interferometry. So basically, if you sent down a signal from space, it travels to the Earth, it interacts and comes back, and the sensor can measure where that signal is along its wavelength when it returns to the sensor, and that is an indication of how far that signal has traveled. If you were to complete another orbit and come back 12 days later and collect the same image from the same place in space, you would expect that if nothing has changed on the Earth's surface, the signal would travel down, it would interact in the same way and come back at the same place and return in the same place in its phase. If, however, something has changed on the landscape, if there's deformation caused either by inflation of a volcano, for example, that lifts up the Earth, or if there's subsidence due to groundwater removal or some other process that causes the ground to sink, that changes the distance that the signal has to travel, which will be reflected as a change in the phase. So if you compare the phase measurements of those two different acquisitions, you can both identify and quantify the amount of deformation that occurred. So that's as much as I'm going to say about phase now. Forrest will be going a lot more into detail on how we use the phase for interferometry, but let's get back to the backscatter. So radar images are formed by processing the amount of energy that's reflected back from the surface. And that the backscatter is the proportion of the sent signal that actually returns to the sensor to be measured. There are a number of different ways that the signal can interact with the Earth's surface. There's specular reflection, which is when the signal comes down and hits a flat surface and just bounces off in the other direction. In this case, there's very little backscatter returning to the sensor to be measured. It all kind of bounces off in the opposite direction. Diffuse scattering is when you have a rougher surface that has angles that are more suitable for returning some of that signal back to the sensor. So the signal comes down, it scatters in a number of directions. Some of that will be angled back at the sensor and be measured. Volume scattering is an interesting concept where the signal interacts with not just a surface, but kind of a volume of surfaces. So a common volume scatterer is a forest. So if you look at the forest canopy, there are lots of leaves, lots of different planes and objects that the signal can interact with. So it's not just hitting one surface and bouncing in one direction or another, it bounces off a series of surfaces. So volume scattering has quite different characteristics than a surface scattering process. Dihedral reflection is a very efficient way of returning the backscatter to the sensor. And that's where the signal comes down, it hits the ground and then hits something else, some sort of vertical aligned object that redirects that signal back to the sensor. So common dihedral reflectors are just buildings with smooth vertical surfaces, or a ship on the ocean, or even tree trunks. And it's actually the way that SAR data is calibrated. There are corner reflectors or dihedral reflectors that are angled maximally to return as much of the signal as possible directly back to the sensor. The amount of backscatter is determined both by the sensor and the target characteristics. So the sensor characteristics that can change the way that the signal interacts are the wavelength, the polarization, the incidence angle, and the look direction of the sensor. I'll be going more into depth on the wavelength and the polarization, but just a quick mention of the incidence angle. As I mentioned, it's all the signal is always coming in at an angle, but that angle can be different from one acquisition to the next. For most of the large agency-driven SAR missions, the point is to have consistent repeat imagery. And in that case, usually the incidence angles are very stable from one acquisition to the next. But there will be a slight difference in the incidence angle from the near range and the far range of the image. So the part that's closest to the sensor will have a slightly different look angle than the farthest away parts of that image. But from one image to the next, that range of incidence angles is always the same. There are other missions that are more targetable or that are a little bit more flexible in their acquisitions. And in that case, you may want to optimize your incidence angle to really pick out the specific feature or process that you're most interested in. But in general, acquisitions are quite consistent. The look direction of the sensor is also important. For most of the large missions, there is a consistent look direction. You have right-looking sensors or left-looking sensors, and it's always pointing the same direction. So if the satellite is in orbit and coming around the Earth from the south to the north, and it's a right-looking sensor, it would be collecting imagery looking off to the east. Whereas when it comes back around and is orbiting downwards from the north to the south, it would be imaging to the west. All of these are important to be aware of because they do change the way that they do change the information that's being presented. And so if you're comparing data sets, for example, the look direction, if you are doing a time series analysis, often you'll want to restrict that to a single look direction so that you're using a consistent geometry and not introducing differences that are caused by, for example, in areas with intense terrain, one direction may be better at imaging one side of the mountain, whereas the other direction might be better at imaging the other side of the mountain. So they can be complementary. You may often want to actually do both, a time series for both direction and then compare them. Because similarly with deformation, because we're measuring deformation in the line of sight of the sensor, if the motion is towards the sensor, if it's looking one direction, it could be much more sensitive to that movement. Whereas if it's looking the other direction and it's moving away or oblique to that look direction, it is not as sensitive to that particular motion that's away from the line of sight of that look direction. So when you're comparing data sets, especially, it's very important to make sure that you're being very consistent with the data sets that you're using. This becomes even more important if you're trying to look across different sensors. Many sensors are collecting in different wavelengths or use different polarizations, and that matters because you may see changes or differences that are not actually due to differences on the ground, but differences in the sensor configuration. For target characteristics, surface roughness and vegetation structure are big drivers of increased backscatter. So the rougher the surface, the more backscatter you would expect to see. And the more complex the vegetation structure, the higher the backscatter you would expect to see. The other component, however, are the dielectric properties of the scatterers on the Earth's surface. So this is essentially the permittivity of a given object. So if you have an object that has high dielectric properties, that means that it's very effective at reflecting the signal. So there's much greater chance of it sending back some of that signal from where it came from. Whereas an object with low dielectric properties absorbs the signal very effectively. And so it may get absorbed into this object and maybe never even make it back out again to return to the sensor to be measured. So you would expect higher backscatter from objects that have higher dielectric properties. One way to increase the dielectric properties of an object is to introduce moisture. So if you have a soil, it may have kind of its own standard dielectric properties, but when you add water to that soil, it increases those dielectric properties. So if you were to image during a drought, the dry soil is much more able to absorb more of that signal. The signal just kind of keeps moving through. This is especially the case in a sand dune or something very, very dry. The signal just doesn't have anything much to bounce off of. And so it just keeps going until the signal extincts. Whereas if there's a rainfall and the soil moisture has really been pumped up, then that soil is much more able to reflect the signal back to the sensor. So you would expect higher backscatter as soil moisture increases. The microwave spectrum, as I mentioned, covers quite a range. Most of the highest frequency bands are not actually used for SAR, especially spaceborne SAR missions. Once you get to the X band, though, that's when the microwave spectrum becomes quite useful for SAR. X has a fairly small wavelength of about 2.5 centimeters, and you can get the highest resolution imagery when you're using X band. C band is very commonly used, and it's a bit longer wavelength than the X band, usually around 5 or 6 centimeters. And then the other really commonly used band is L. And this is one of the longest bands that is commonly flown on spacecraft in particular. So that has a wavelength of around 25 centimeters. And for those of you who are familiar with the NISAR mission, which is kind of, we're preparing you for using NISAR data, the NISAR mission will have an L-band sensor that collects data globally, but it also will have an S-band sensor. And this is quite unique. There aren't a lot of spaceborne SAR sensors that do have S-band. So NISAR will have the S-band sensor that's mostly going to be collecting data over India. So in those areas, you'll have both L and S-band to compare. And then P-band is also sometimes used for SAR. It's a less frequent band to use on spaceborne SAR missions. That wavelength that is used by the sensor really makes a difference in terms of the penetration ability of the signal. So an X-band sensor cannot penetrate very far into the canopy, especially if you had large leaves. It's only a 2.5 centimeter wavelength. A leaf can be, the size of your hand, and so it becomes very difficult for the signal to kind of move through between those leaves. So generally with an X-band sensor, you're getting information about the top of the canopy when you're looking at vegetation, whereas C-band can penetrate much more deeply into the canopy. And so you're getting information from more of the body of the canopy. L-band, on the other hand, with a 25 centimeter wavelength can pass through much of that leafy structure. And in many cases, it's actually interacting more with the structure of the tree. So the tree trunk, some of the larger branches, and may actually be even providing information from the forest floor or any structures that might be underneath the canopy. The same thing holds with soil. So if you have an X-band sensor and it's bare soil, you're getting information mostly about the surface, the closest to the surface parts of the soil column, whereas C-band gets a little bit deeper. And then if you're interested more in like the root level of the soil column, then the L-band sensor is more likely to be able to give you more information about what's happening a little bit deeper. So just a quick visualization of the difference between the acquisitions from different bands. On the left, we have this X-band acquisition, and you can see it. You're looking at the top of tree canopy. You're really seeing the vegetation mostly. Whereas the P-band, which is one of the longest bands that is used for SAR, you're actually seeing structures, buildings, and infrastructure that's underneath that tree canopy. And in fact, there are all these bright dots along here, and that's the signal interacting with the tree trunks. So you're not really seeing much information about the actual canopy itself. It's what's beneath that canopy.
Hey, Heidi,
so
we just had a question come in over chat, which is if P-band has the most penetration, why are most SAR satellites not at P-band?
Well, so it depends on what you're interested in looking at. And also P-band with that very long wavelength sometimes has difficulties with other radio frequencies. It can be there can be some interference. So it's mostly used for biomass. So if you really do want to make sure that you're hitting the floor of the forest, and then, for example, using X-band so that you could see kind of the difference between the phases of those two different types of wavelengths, you can use that to calculate biomass. But in most cases, the L band is a bit more of a robust wavelength that's useful for kind of a wider variety of applications. SAR sensors can be configured to collect data using different polarizations, and the polarization refers to the orientation of the electric field of the signal. So most radars are designed to transmit and receive in either vertical or horizontal polarization. So polarization is usually indicated by two letters. The first is the transmit polarization, and the second is the receive polarization. So if you're sending out a horizontally polarized signal and only measuring the horizontal returns, you would have an HH polarization. If you're sending it out in a vertical polarization and only receiving the vertical returns, that is a VV polarization. If you're sending out in horizontal and measuring the vertical returns, that would be HV. And then oppositely, if you're sending out in vertical polarization and receiving in horizontal, that would be VH. There are some sensors that have full quad pol capabilities where they're collecting all four of these polarizations, but that's a very compute heavy process. It's a lot of data to collect and also transmit down to the earth. And so usually quad pol acquisitions have the trade-off of not having as large of a footprint. So you're collecting less data, but getting more information about that area. Because of that trade-off, most sensors, especially the larger missions, don't regularly acquire in full quad pol modes. Most of the larger missions tend to have a dual pol approach. So for example, Sentinel-1, over land, it's sending out a vertical signal, and it collects returns. It measures returns that are both still vertically polarized and also the horizontal returns. So you would get VV and VH over most land masses. And then over the water, it's sending out in horizontal polarization and receiving in a vertical polarization, or in both horizontal and vertical. So you get the HH and the HV over the oceans, but it doesn't ever collect all four at the same time. Some sensors also are just single pol only. Some of the smaller satellite missions that are more taskable, many of those are just a single pol acquisition. So it's just VV or HH. The different polarizations interact differently with the Earth's structures. So for surface roughness, which I mentioned is a big driver in the backscatter returns, the VV polarization is most sensitive to that surface roughness. So if you're looking at VV returns, you would expect that increases in backscatter would either be due to surface roughness or increased soil moisture. For the HH polarization, it's most sensitive to double bounce. So all of this dihedral reflection that's bouncing off buildings, or if you're looking at ships on the ocean, for example, HH is very sensitive to that sort of those vertical structures on the landscape. For volume scattering, where you're interacting with these complex structures, HV and VH are the commonly used indicators. They're most sensitive to volume scattering. And this is because when the signal is coming down, it's interacting with that complex series of leaves and tree branches and all of that stuff. Not only is it bouncing around, but it also is sometimes depolarized. So it actually the polarization gets changed around. And that's why some of the returns then come back not in the original polarization, but in the opposite polarization. So if you're looking at VH imagery, you would expect that areas with vegetation would have higher backscatter. And the more complex the vegetation, the greater the backscatter. So just a quick visual review. Here we have a lake that's, this is a very calm day. And surface water, when it is flat, so if you don't have any wind, it's an excellent specular reflector. So you have the signal coming in, it's hitting the water, which has very high dielectric properties, hits that water and bounces off in the other direction, never to be returned to the sensor for measuring. So in general, if it's calm, you will see very low returns from surface water. Now that changes if you have wind, and this is particularly true with the VV polarization. So if you're looking at a VV data set on a windy day, the lake can actually look just as bright as the surrounding terrain. In some cases, if it's windy enough and the surface is roughened up enough by the waves. So that's important to be aware of. The VH is not as much impacted by the surface roughness. It's still just a surface, so it's not changing around the polarization much. So you would still expect very low returns in VH, even on a windier day. Urban areas, like over here, you've got these buildings that tend to have very bright backscatter just because of all of that dihedral bouncing. So it's redirecting the signal back to the sensor. And this is particularly true if the buildings are oriented in the direction of the incoming signal. So in some cities where there are different orientations of different neighborhoods, you might have one area that has the buildings predominantly oriented in one direction, and then another one where it's kind of turned. And in some cases, you can see that difference by the differing brightness of those neighborhoods, just because the angles are really auspicious for returning that signal very brightly, whereas the other one, the angles aren't quite as perfect for getting as much of the signal back. So that's a really interesting phenomenon. For the forest, again, we would expect higher backscatter for VH when there's forest canopy, but also in VV, you may see increased backscatter if it's a very rough surface. You know, if it's an irregular leafy surface, you would expect higher backscatter than, for example, the surrounding fields. So here we have a kind of a range of fields, a little patchwork. And fields can really differ from one to the other based on the stage of growth. So a freshly plowed field will have different responses than a field that has vegetation already growing on it. And then also the soil moisture can really vary from one field to the next, especially in areas where irrigation is employed. If there are some that are actively being irrigated and others that aren't, you will see that difference very strongly in the image. So as I mentioned, there are certain distortions that are inherent to SAR data sets. And if we look at the image on the left here, this is an area outside in Southeast Alaska that has a lot of tall mountains. If you look at the image, you can see that the mountains look kind of squashed over with a bright leading edge. And this goes back again to those angles that are involved. So you have a mountain slope and you have a signal coming in, and it's possible to be receiving returns from near the bottom of the mountain and near the top of the mountain coming back to the sensor at about the same time. And so the sensor interprets that as being from one place on Earth, even though it's an entire mountain slope that's contributing that backscatter. And so radiometric terrain correction uses a digital elevation model to correct for this distortion. It uses the DEM to move the pixels into place so that the tops of the mountains are where you would expect them. And it also normalizes the backscatter based on the actual surface area of the slope that's contributing the signal back to the sensor. So once radiometric terrain correction is complete, you can see that as you're looking down from space, the mountains are where you would expect them to be. And also the front sides and the back sides of the mountains are much more similar in their backscatter. So RTC is particularly important if you want to compare the data sets to something else. So if you have an optical data set or some other types of imagery that you want to compare your SAR data to, it's really critical to do that radiometric terrain correction so that the features align. If you were to bring in, this is a GRD, which is a level 1 product from Sentinel-1. If you bring that into your GIS environment, it shows up in the right place, but you have all of these distortions in the mountains, and it will be even more important if you have a lot of terrain in your image. So when you bring in an RTC product, then it aligns well. You can align it also with in situ data if you have geospatial points that you want to align with your SAR imagery. That's where RTC becomes particularly important. In terms of the phase, a common way of using the phase measurements is for InSAR. And basically you're using a pair of acquisitions. So you need 2 different acquisitions from the same place in space over the same footprint on the Earth's surface. And you can compare those phase values from the 2 acquisitions, and you get an interferogram that allows you to identify and quantify surface deformation. So the closer the fringes are to each other, the higher the amount of deformation, and you can actually then use the fringe spacing to calculate the amount of deformation in the line of sight. And with that, I will pass it back to Alex to talk about Vertex.
Thanks, Heidi. I'll just share the screen again. All right. So before we dive into Vertex, I'll just give a little description of what ASF is in case anybody isn't familiar. So the Alaska Satellite Facility is one of 12 NASA DACs. So these are distributed active archive centers. And so the DACs host, archive and host and distribute data for not only for NASA, but certain data sets also from, in our case at ASF, from ESA, JAXA, and the Canadian Space Agency as well. So most of the DACs are specific to a field or an area of study. So you can see that, there's the LP DAC, the land processes DAC, focuses on many different land processes. There's the physical oceanography DAC that focuses on on oceanography. The Alaska Satellite Facility differs in that sense, in that we are the only DAC that is sensor specific, because SAR is a difficult data set to work with. It was decided that it would be most useful and helpful to users of SAR if those data were all hosted in a single DAC, so that we could provide information on how to leverage those products, such as delivering educational materials and workshops such as this one. And so in order to provide an easy way to identify different data from different data sets that might be useful to users, we've developed a web app called Vertex, which is our search tool. And so this QR code will take you to Vertex. If you've found your way to the slide deck, there's also a link right here. And in order to download those data and in order on-demand processing, you will need an Earth Data login, and you'll need to accept the end user license agreement for ASF data products. And so that process is described in our preparatory slide deck for this workshop, which you should have received an email link to, and is also linked earlier on in the intro to this slide deck. And finally, before I jump into a demonstration of the different search options and tools in Vertex, I do want to point out that there are some tutorials on doing exactly this. So for ordering RTC products and ordering SBAS stacks of InSAR products as well. And so you can find these in the slide deck here. So if you wish to put together your own SBAS stack for tomorrow and are having trouble remembering all the details that I'm about to present, you can find your way to this to these resources here, and I would use the InSAR on-demand story map, which will walk you through putting together an SBAS stack as well. So now I'll hop over to Vertex. And so when you jump into Vertex, it defaults to a geographic search and the Sentinel-1 dataset. However, there are a number of datasets that you have access to from ESA, JAXA, NASA, and the Canadian Space Agency. And so there are a whole host of datasets, a few that I'll specifically point out that might be of interest, especially given in the context of NISAR, are the UAV SAR data. So these are L-band data collected from UAV SAR, which is NASA's airplane for collecting SAR data, and so these are L-band similarly to NISAR, and they've been downsampled to sort of mimic a NISAR-like product. Also, there are the ARIA S1 GunWs, and so while these do not look like a NISAR product, they are formatted in the same way that NISAR data will be formatted. So if you're developing workflows that count on your data being in a NISAR format, then this would be the data set to work with. Although you won't get the same results, of course, because the data themselves are not similar. It's just how the data are formatted. And then a new addition that's still in beta are S1 bursts. And so Sentinel-1 scenes are acquired in 3 swaths, each containing 9 to 10 bursts of data. And while the bursts are geostationary, the scenes are not. So if you collect scenes over the full time series of Sentinel-1 data, you may notice that there is some shift in the boundaries of those scenes. However, if you're working with bursts, those are geostationary, that they will not shift around on you. Presently, we offer on-demand processing for Sentinel-1 scenes, and we do not yet offer any on-demand processing for bursts, though that may come in the future. So today, for the purposes of this workshop, we'll be working with Sentinel-1 data, full scenes of Sentinel-1 data. So I will leave that on Sentinel-1, and then I'm just, before diving into identifying a reference scene and creating an SBAS stack from that, I'll just go through some of the other search types. So we have a list search. So if you already know the scene IDs for a certain scene or set of scenes, you can just paste those into the list search here. And I'm hiding my search button here. Here we go. And then search those specific scenes. You'll notice whenever you search, whenever you have search results in Vertex, the products appear on the left, and you can click around between the different products, and you can download those products by adding them to your download queue here. So you can see that now I've added 5 products to my shopping cart here, and I could download those data individually by clicking these buttons here, or I could also retrieve a Python script that would download every product in my my shopping cart. If if I had hundreds, that might be the more convenient way to go. For now, I'll clear this. You'll also notice that I am logged in. And so in order to download data, you will need to log in using your Earth Data login. And you'll have had to accept the EULA for ASF data. Another thing to note when you've searched a product is that there is a scene detail in the center pane here. And so this gives some helpful information related to a given product, including, in this case, the beam mode, the path, the flight direction, depending on the data set. You may see a frame ID as well. So that is the gist of the list search here. I'm going to skip over the baseline and SBAS search for now. I'll get back to those in a minute. There's also an event search. And so this is pre-populated with a host of already processed RTCs and interferograms for a selection of volcanic and earthquake events, seismic events around the world. This does not contain, all volcanic activity and seismic activity in the world, just a subset of events. And so once an event has been added to this tool, its data are collected over that area, extending into the future. So typically, this will show some pre-event data and then data extending into the future. And so you can select a different event by simply clicking on on a little icon, and so you can see that that we have volcanic events represented with this little icon with volcano, and then the little wave here for seismic activity. And so you can also just scroll through the list of events on the right, or on the left rather. There are 168 in total currently. And when you click on a new event, any products appear on the right, and then the event detail appears in the center. And if you click on the event detail, you'll pop out a handy file explorer here, which will allow you to view the browse images for for all of the data products in this event. And you can then download these files directly from search results here. You can add numerous files to your shopping cart. And then you can also order reprocessing of these events. And so this little stack of squares here, this icon, is the ASF HyP on-demand processing icon. And so if I wanted to order a new interferogram that would be attached to my my personal account, then I could add that to my on-demand queue. You'd see that this is now in my on-demand queue up here. I'm going to show you more about how to order products from HyP shortly. So for now, I'm just going to clear this this particular product from the queue. And then we also have a number of derived data sets. And so if you click on one of these, one of the information for one of these data sets, it will take you to a page that provides more information about that data set, including information on on common applications, and it will explain how to cite that data from that particular data set, and it will show you where you can download those data. Okay, so now that we've kind of gone through some of those some of the other search options, I'm going to focus on the search options that you would want to use to build a small baseline stack of interferograms for an SBAS InSAR time series. So initially, we will need a reference scene from which to build our SBAS stack. And so here in a geographic search, you see you can just kind of pan around. You'll notice that there are some products selected. So it looks like I have an active search from a previous search still in place. So you can clear an old search by selecting the little arrow here next to the search option and just clear the search. And you'll see that I am now ready to start drawing a bounding box around a particular area. And so I guess I'll select an area around New Delhi. And so now I've dropped a bounding box here. If I wanted to change that, I could just click around. If I had already searched and I no longer had the option, if I didn't see the little icon that said click to start drawing, you can always get that back by coming over here and clicking on draw a box or draw a polygon. One caveat, if you're drawing a polygon, it's best to minimize the number of points. I don't know the exact number, but there is a limit to the number of points that you can drop when creating a polygon in Vertex. Typically, if you're just looking for scenes that are going to intersect a rough area, the easiest thing to do is to just draw a box. And so, yes, I'll drop my box around New Delhi here. And so if I were to just click search now, it would identify, it looks like 7,664 files, and it would only display 250 of them. And those may not be any of the products that that I was interested in. And so so I'm going to start by since I'm using this to create an SBAS stack, I'm going to start with a date range that's sort of constricted to the start of when I would want my time series. And in this case, I'm just going to select the start of 2021. And it's important that you provide it at least 12 days of in your time range, and that's because for Sentinel-1 there's a repeat orbit of 12 days. So in order to ensure that you've gotten at least one scene that intersects this area in every orbit that intersects this area of interest, you should drop in at least a 2-week or a 12-day or 2-week period here. There are additional filters that you can put in place. So you can select the SLC. In this case, we'll want a single complex for building our interferograms. You can select the beam mode. We'll want IW. In many cases, you may not need to select the beam mode. I believe that Sentinel-1 did use some other beam modes early on in the when it was first launched. Although I think at this point most of those acquisitions are in IW already. You could select a polarization, an orbit direction. I'm just going to leave those blank for now, and then I'll click search. And so now we've only got a handful of files here, and you'll see that that I have a couple paths heading in different directions. And so if the red box here is the selected scene, which corresponds to the highlighted scene on the left. And if I look at the scene detail, I can see that is in the descending orbit direction. And if I were to click on a scene that's kind of facing off in a different direction, you'll see that is in the ascending orbit direction. In this case, I only have a handful of scenes, but if I had not limited my date range, or if I had a much larger bounding box, it could be that I had hundreds of scenes in here, and it can be a little bit difficult at times to select the scene that you that you want. If you have many bounding boxes that are kind of overlaid on top of each other. And so if that happens and you wish to eliminate some of these scenes so that you can navigate a little bit better and cut down on the number of scenes in your results, you can go back to filters and you can define the path and or frame to help limit those. So in this case, I'm looking at path 27 in frame 86. And if, for example, there were hundreds of scenes here and I was having a hard time selecting the particular scene that I wanted, and I didn't want to scan through hundreds of scenes on the left here to find it, I would just go in and set path 27 in frame 86, and then update my search results. And now I only have that single scene. So at this point, I could create, so this is the SLC. I could create an RTC. I could add an RTC job to my on-demand queue. However, we're creating an SBAS stack full of interferograms. I could take this scene name and see my options for creating an individual interferogram from this reference scene. And to do that, I would use the baseline search. And so I'll just show you that really quickly, even though that's not what we're going to actually be using for our purposes today. So I would paste in that scene name in the baseline search. I believe there's also a button in the scene detail. When we get back to the other screen, I can point that out. Okay, and so now that I have pasted in my reference scene, you can see that there are, it looks like 228 other scenes that I could pair this with in order to produce an interferogram. And this plot on the right here shows you the perpendicular and temporal baselines. So the temporal baseline refers to the time between those acquisitions. So the number of days between between my reference scene in black here, and right now I've selected a secondary scene that looks like it is 72 days. It was taken 72 days later. And then the perpendicular baseline refers to the difference in location and space of the sensor. So this particular scene that was taken 72 days later, you can see that it also was separated in space by 42 meters from the original location of the sensor when the reference scene was taken. And so to add any of to create interferograms with any of these, you could identify a pair here, and then once again select the little HyP logo, and then I could add an SLC pair, and so that would produce an interferogram. Oh, and I should mention that both the RTCs and the InSAR processing that you can do with HyP are produced using Gamma software. If I wanted to create every possible, all 228 interferograms, you could also add these to your on-demand queue in bulk with the on-demand button at the top of the search results here. I could add all 227 pairs if I wanted. But we are going to create an SBAS stack, so I'm going to head back to the search results for my geographic search, and here I had my single pair that I had filtered down to, and then this is the button that I was talking about. I didn't necessarily have to paste the scene name into the baseline. Once I had identified and selected the scene, I could just have clicked the baseline tool to have ended up in the same spot. Oops. Great. And I can do the same for an SBAS stack. So I'm going to select the SBAS button here, and this will use that reference scene to start building an SBAS stack. And so this is going to pull up every possible scene that could be used in an SBAS stack. And you'll notice that I have no search results here. And the reason for that is that when I selected the SBAS button, it carried over the date range. And because I only have a 2-week date range in here, it didn't have any secondary scenes to pair with it. So the first thing I have to do is extend this date range. And I'm going to give it a full 2 years. So I'm going to go from January of 2021 all the way to the end of December of 2022. And now you'll see that we have some connections here. And so each of these points on the graph represent a reference or secondary SLC. And then each edge is the interferogram produced with the reference and secondary scene. And so here you can see that we do have, it is all connected, but it's not very interconnected. There are no triangles. There are no connections, for example, from this scene to this scene. And when you're building an SBAS stack, you really want you want some of those extra connections because of the presence of closure phase ambiguity. I believe Forrest will get into this in a little bit more detail. I don't want to misspeak here. So, but it is important to have not just a single line of connections. You really want an interconnected web of interferograms in your stack. And so you'll notice that there are slider bars for changing the perpendicular baseline and the temporal baselines. So I'm going to bump this up to 36 days, and now I'm starting to see a lot more connections in this stack. And if I wanted to reduce the perpendicular baseline, I could also do that. And so on occasion, you may select an area where you regularly experience decorrelation during a given season of the year. You know, in snowy regions, often that is wintertime, and so it's helpful to remove the interferograms from those particular seasons. And so you can do that using a seasonal search. And so you can define a season here. And so I'm just going to sort of randomly create a season, which may not be applicable to this area at all, but just to show the how you would do this. You know, you can set your season start and end dates here. But now you'll notice that I have two disconnected stacks. So while I've taken out those problematic interferograms that may have been decorrelated, I now have a gap in my stack, and I have two disconnected stacks. And so if you're trying to bridge across a season that experiences heavy decorrelation, you'll probably want to add some custom pairs containing a much longer temporal baseline. So you can click on the little custom pair button here to add a paired little plus, and then you can select your reference scene and then a secondary scene. And you can continue adding pairs that bridge the season that you've filtered away. And so in this way, you can create your connected stack that covers multiple years and does not pull in those data that have a tendency to decorrelate. Another option in the SPAS search filters is the overlap threshold. As I mentioned earlier, Sentinel-1 scenes do experience some frame shift over time, and so if you're developing a very long time series and there is substantial frame shift, it's possible that that some of these scenes that you're creating don't actually overlap, like both in terms of when individual interferograms, which is what this overlap threshold will filter out. If there wasn't overlap, if there was no overlap, or or less than 50% overlap, depending on which option you select, then you can filter out those scenes. However, even after doing this, because of the frame shift, you may have created individual interferograms that contain enough overlap, but just warning, you may see that over the entire time series, over your entire SPAS stack, you may only have a small area of common overlap through the entire time series. But you can at least minimize and filter away individual interferograms that don't meet your minimum requirements for overlap. So once you've sort of tweaked and determined your ideal small baseline stack, and you're ready to order it, you can once again add those individual pairs here using the little HyP button here, adding SLC pairs. Although in this case, most likely you'll want to add all of your scenes, and so you can see that that this has created 127 pairs from 47 different scenes, and I'm just going to add the entire SPAS stack to my on-demand queue. And so if you click on your on-demand queue, you'll see that all of these interferograms have been added. And then you'll also notice that there are some different options and auxiliary products that you can request to have included. MintPy does require the DEM and the look vectors, and to just make this really straightforward and simple, we've added a Set MintPy Options button. So if you're working with a MintPy time series and you want to ensure that you have all of the products required to run that time series in MintPy, just click that little Set MintPy Options button, and it will click the DEM and the look vectors, so you don't have to remember which of those products are required. You can also select to have water masked out when doing the interferometric processing, which can be useful or not, depending on your area of interest here. In this case, I've selected New Delhi, so it probably doesn't really matter. I'm just going to leave that turned off. You can also select different look options. I'm going to leave it on the default of 20x4, and then I will submit my 127 jobs. And when I do that, it will pop up and request a name for the project. Now, one sort of minor warning here: if I didn't put in a project name and I just submitted the 127 jobs, they would be submitted, but they would lack a project name, and so they would become harder to associate with each other in my HyP account when I was searching for those products later. I highly recommend adding some sort of name, just to make it stand out, or to make it recognizable when you're searching for those data later. And so then I'll hit my submit button, and and I should point out that there are that each HyP account comes with a monthly quota of 1,000 jobs, And so since I just submitted 127 jobs, if I look at my on-demand queue, and I had also submitted some additional jobs yesterday. So my quota has been knocked down to 721. So if you want to see what your current quota is, just open up your on-demand queue and you'll see that information at the bottom. So now that I've submitted my jobs, I can go and check the status of those jobs. And so to do that, I'll head over to the on-demand products. And it looks like we're about at break time, but we're almost done here. So I'm just going to wrap this up. And so now you can see that I have all of these pending jobs. And at some point in the near future, this will change to processing. And then once they are finished, you'll see that they turn up here ready to be added to my download queue. And so I could add finished jobs here to my download queue and then head over and download them. But it's much more typical to access these data programmatically. And so HyP, both HyP and Vertex contain Python packages for interacting with their APIs. And typically when you're downloading your full stack of your full SBAS stack, those would you'd want to just pull those in with the with a script leveraging those Python packages into most likely onto a cloud compute instance, such as an OpenSAR lab account. And so one other note before we finish out this section, HyP does have a 2-week window during which these products will be available. After that point, they will expire. So if I scroll further down my on-demand queue, you'll see that I do have some old expired products. And if I wanted to reprocess those data, I could add that pair. And I believe there's also, if I click on the little expired button here, I could resubmit that job, or I could resubmit the entire project. If I had a full, stack of data and I wanted to reprocess that whole stack, I could just resubmit the entire project. All right, and that about wraps it up for our introduction to Vertex. And so now Forrest is going to kick us off with an intro to InSAR and using HyP.
Sure. I know InSAR is an exciting topic for a lot of people, so happy to tell you a little bit about what I know on the topic. So I'll go ahead and start up the share here. All right, how's that looking, Alex? Good?
Yes, yep, it looks
awesome.
good.
Well, just to give you a brief overview of what we're going to be covering, first we're going to go into how the basics of InSAR, how it works, what applications InSAR has, some specifics on InSAR for deformation monitoring, some information on InSAR phase components, a brief discussion of coherence, and then finish with discussing of unwrapping interferograms, a important part of InSAR that often kind of just gets pushed to the side because it's hard. So just to start off, let's talk about what InSAR is. InSAR stands for Interferometric Synthetic Aperture Radar. And you can think of it as a difference between two SAR images. You're basically comparing what one SAR image looks like to another while specifically looking at the phase component. And so, as you can remember from Heidi's talk, all SAR measurements are made up of two components, the phase or component and the amplitude component. The amplitude component is kind of what we have over here, where you can you see something that looks a little bit more similar to actual land, where you can see like a slight mountain and some divots over here. But then the phase component, when you look at it in a raw SAR image, is often just looks like white noise or random values. And that's because the phase component is highly variable from place to place. And the reason that is that when a SAR signal is traveling from the satellite to the Earth, it goes through many, many, many different phase cycles. So on the order of millions to billions, I'm not quite sure. But the phase component is telling you, okay, once the SAR signal has traveled all the way back down to the Earth and come all the way back, what is the phase of the returned wave on a 2 pi scale? So basically, it's some modulo distance between the satellite and the ground. And because we lump off all of the full cycle values, we only have information on basically the final partial phase cycle that the signal transpires. And because of that, very small variations on the ground lead to random noise. And so in general, people don't use the phase component of a single SAR image. What they do is combine them. So even though this phase signal looks rather random when you look at just one SAR image, if you take one SAR image and multiply it by the complex conjugate of another SAR image taken at the same location or at a different time, what you'll see is that you actually start to see signals in the data. And that's because while the phase value varies significantly in space, say between this point in the image and this point over here, they tend to stay rather consistent in time because the distance between the satellite and the Earth is fairly consistent. And so by taking the complex conjugate or looking at the difference between the phase in two images, you can start to resolve some information about the distance of the satellite to the ground or other metrics along this line. And what's important to remember about InSAR is that in order to measure some sort of difference with InSAR, there has to be some sort of difference between the first SAR image you're using and the second SAR image that you're using. And there are two major types of differences that you can have between two SAR images when performing InSAR. You can have either a large difference in the perpendicular baseline. Basically, when the SAR signal is captured, there's going to be a difference in the place that you're looking at it from, but at the exact same time. Or you can have SAR images taken at the same location or very close to it, but at different times. And in that case, you're measuring a different thing. So when we talk about these different, we call them baseline types. This table shows you a little bit of the types of differences we can measure. So the first type of difference we can measure, as I discussed, is a difference in where you could basically create two SAR images at the exact same time, but from different places. And what this causes is a difference in the incidence angle of how it hits the Earth. And so this type of InSAR is typically called a cross-track InSAR. And by using this type of InSAR, you can measure something about the Earth's topography. And this is the type of analysis that is used to create digital elevation models. A notable mission that used this technique would have been the NASA Shuttle Radar Topography Mission, or SRTM. If you've also heard of Tandem-X, which is run by the German space agency DLR, they also use this technique. Then the other type of measurement that we can make using a difference not in the location of where the signal was captured, but a difference in the time that it was captured. Basically, take one image, complete an orbit, and come back 6 days later and take another image. We can use that difference in time to say something about the actual deformation of the Earth. And this you will sometimes hear called differential InSAR. But this is probably the most common form of InSAR, so many people just call it InSAR and leave off the differential component. And this is the type of InSAR most people are interested in. This is the type of InSAR that you would use to measure volcanic activity, the motion of the Earth due to earthquakes, or even something as small as landslide activity. And an important thing to remember is that the type of deformation you're measuring is really closely tied with how big of a difference in time there is between your two images. So a difference in a few days will allow you to generally capture faster motion. So that's used for glacier movement, ice fields, lava flows, things like that. But if you have a time difference of many days or even a year, you start to measure things like subsidence, seismic events, volcanic activities, things like that. And so for reference, the satellite that most people are using for InSAR these days is the Sentinel-1 mission. Typically you get images of the same location every 12 to 48 days on repeat. So that makes it good for these types of subsidence, seismic event things, and makes it a little bit more difficult to capture those glacier or ice fields. I believe that NISAR globally is going to be captured with a 12-day repeat. So every 12 days you will get another SAR pass, which will make it also really good for these subsidence, seismic events type of InSAR analyses. So we talked a little bit about the phase difference that InSAR is measuring, but here is a specific example for a deformation InSAR or differential InSAR application. So here we're taking an earthquake as an example. So pre-earthquake, we have our SAR satellite up here sending some signal back to the ground, and it makes a measurement of the phase of that wave when it is returned up to the top. Represented here by, I believe this is psi. So psi of the first image, which will be the phase. And then after the earthquake, there is some deformation on the ground, which causes the distance between the satellite and the ground to actually be slightly longer. And in this case, that's the phase difference that we're measuring with InSAR or interferometry. And so we have the phase represented here by psi of the second image. And then in order to compare those two SAR images, we take the complex conjugate of the two in order to calculate this phase difference. And then we can relate this phase difference to the actual deformation on the ground using this formula, where basically the change in distance between the satellite and the ground, represented here by delta R, is equal to lambda, the wavelength of the SAR sensor that we're using, divided by 4 pi multiplied by the change in the phase between the two images, which is the complex conjugate component. And a really important thing to remember here is that for InSAR, we're always measuring a change in range between the satellite and the ground. That means that the deformation we're measuring is in the line of sight direction, which Heidi mentioned a little bit previously. And so an important thing to remember here is that because we're measuring along a satellite's line of sight, and our SAR satellites tend to be looking either off to the left or off to the right by 20 to 30 degrees, we're not measuring true up-down motion or side-to-side motion. And this can lead to some interesting characteristics. In particular, most satellites will have an ascending pass and a descending pass, one where they're moving up towards the North Pole and one where they're moving down towards the South Pole. And in these contexts, if you compare InSAR images of the same event, but taken from those different orbit passes, either ascending or descending, the deformation pattern will look very, very different because of the fact that you are using a different line of sight when you're actually making the measurement. So once we've done all that, the image we're able to produce using the complex conjugate is this image right here. And this is what we call an interferogram. And for those of you a little less familiar with looking at interferograms, they may look a bit strange. But the important thing to remember here is that because we're measuring phase differences, our phase differences are always going to be somewhere between negative pi and pi, or basically in one cycle. Unfortunately, many deformation patterns are more than one cycle. And so what happens is we measure deformation of one full cycle going from negative pi to 0 to pi, and then we drop back down to negative pi again. And that causes a effect in interferograms that we call fringes, or basically a repeating pattern of deformation values as we move through zones of deformation. And I'll have a graph a little bit later that kind of illustrates a little bit more clearly, but just to point out what we're seeing in this image. In this image, very dark blue colors are going to be a value of negative pi, and very bright yellows or reds, reds will be positive pi values. And so what we're seeing here is, in here we have the center of deformation for this earthquake. And so in order to actually count how much deformation has occurred in this zone, we can count the number of fringes, or the number of cycles of deformation we went through throughout this pattern. So for instance, here we can see we have an area of dark blue. And then as we move in towards the deformation in this direction, we go through the full cycle of colors in this interferogram, from blue to teal to yellow to red. And then we begin back over at blue. So that's one full phase cycle, or one cycle of deformation, which in this case, if this were a Sentinel-1 interferogram, would be about 2.5 centimeters of deformation. So if we continue counting in, we go blue to teal to yellow to red again. That's another full cycle, or another 2.5 centimeters of deformation. And then we can keep counting. There's another. So just estimating, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 full cycles of deformation in this location. And that means from a stable reference point, say out here, we have roughly 25 centimeters of deformation near the center of this deformation pattern here. So while actual movement of the Earth is one major way that we can get deformation in a SAR image, there are a lot of other components that can change the phase to vary between two SAR imagery collects. And it's important to keep those in mind when working with InSAR data, because they will often lead to problems that you have to account for. So in particular, we have, this represents the total change in displacement, or the total change in the phase between a first collect from a satellite and the second collect of a satellite. And so what we see here is, the first parameter here is the actual signal that we often care about, or the change in the distance from the Earth's surface to the satellite sensor, which is our change in displacement. As the refractive index of the atmosphere changes, typically due to changes in the ionospheric total electric content, or in the water content of the troposphere, we'll get slightly different refractive indexes in those areas, which can change the speed of the signal at those points, leading to a change in phase. The next thing is, because we never are able to put the satellite exactly back in the same place on repeat orbits, we do have some component of the change in phase that is related to our change in our perpendicular baseline, or basically the type of InSAR that you would use to measure elevation or create DEMs. So we have a small component of the actual phase change related to that, which we have to account for. The next is, as Heidi mentioned briefly, scattering can significantly change the characteristics of a particular site. And in particular, in areas where you have vegetation, where there is volume scattering, even a rearrangement of the leaves or the branches of a tree due to the wind can change the overall scattering properties of a given area. And these slight differences can lead to very different paths that the SAR signal takes on its path to the ground and then back up to the satellite. So this can induce a phase change that we often have to account for. And the final is phase change related to noise. Typically, this is due to the very slight sensor inconsistencies or other errors in our processing that we have to account for. But this is typically a random component that we aren't able to easily model. And so in general, it's good to keep a handle on what the general size or magnitude of these different effects are. So typically with the type of SAR satellites that we're flying today, this displacement component that we can measure is typically in the order of millimeters to centimeters, while the atmospheric component can be a few centimeters to even tens of centimeters. So a much larger magnitude in the actual deformation signal that we're trying to measure. So this will be a component that it becomes very important to correct for when we're looking at our data. Similarly, the geometry can induce changes on the centimeter level, but luckily we generally have pretty good models of how to correct for these. And then our scattering can lead to changes in the order of millimeters. And then generally this noise component is relatively low. The thermal noise component, at least of it, is relatively low, but then processing errors can add more. But in general, this equation is dominated by the first four parameters, and our noise for a well-designed system is relatively low. Now, as you can see, there's a lot of things that affect the overall quality of an InSAR measurement. So it's important that we have some measurement of the quality of a given interferogram. And what we use to calculate this is something called the coherence. And this coherence is it's a quality measure of the similarity of neighboring pixels in an interferogram and a measurement of the quality of the similarity between the first SAR image and the second SAR image used to perform to create that interferogrammetric pair. So once again, here are our general contributors to the noise. We have receiver noise due to the designing of the system. We have propagation effects such as the atmospheric component that we discussed earlier. We have the temporal changes of the scattering conditions, say due to the waving of trees in the wind or a rearrangement of their leaf structure. And then we have process errors that crop up due to issues that we've introduced in the software that sometimes happen. And then from that, we can then calculate this parameter called coherence. And coherence is typically ranges from 0 to 1 and is calculated using this formula up here, where basically what we're doing is for a local window, we're taking the complex conjugate of two SAR images, very much like how we form an InSAR pair, and then taking the magnitude of that. And then we divide that by the magnitude of the SAR image, of the first SAR image, summed for the local window, and squared, multiplied by the sum of the magnitudes in the local area in the second SAR image squared, and then we take the square root of that component of the equation, and that gets us our final coherence. And if people are more interested in how coherence is calculated, there's another notebook I can point you to that goes a little bit more in detail. But the important things to remember are always that coherence varies from 0 to 1, and that in general, higher values indicate higher coherence and a higher quality InSAR image. And it's very important when you're doing analyses to always pay attention to what the coherence is in the area that you're working, because in general, you should be very cautious when making interpretations of interferometric data if the coherence is very low in that area. And when we go on to actually discuss time series InSAR, we'll look at different ways that we can make sure that we're only including high quality, high coherence data in our analyses. So now that we have our measurement of our interferometric phase and our coherence, we now finally need to get from a wrapped InSAR image into a deformation field that we can actually use. And so, as I mentioned earlier, here's another example of an interferogram, but here in grayscale. And so here we can see that the color scale goes from black for negative pi all the way to white for pi, which is basically one full phase cycle of deformation. And so we can see that deformation is increasing as we get towards the center of this earthquake feature, but that it's not a continuous field of deformation that we're measuring. Instead, we're measuring this strange kind of wrapped phase component. So if we were to think ideally about, okay, what does the deformation field in this area look like? We would expect something more like this, a line that as you move in towards the site of deformation, steadily increases as deformation starts to increase towards the center. Unfortunately, InSAR typically only gives us a measurement of the wrapped phase, or basically the phase that has been chunked into these negative pi to pi bins. So an actual deformation phase that looks something like this, a steadily increasing line, would be represented in an interferogram as something like this, where you increase from negative pi to pi, drop back down again, start out from negative pi to pi again, and drop back down, et cetera, et cetera, et cetera. And what we're really trying to do is get from this wrapped phase view of how InSAR works into a view of the actual phase, which we often will call unwrapped phase. And typically, the way that we do this is using a process called unwrapping. And this is an empirical process that uses statistics and other information about the interferometric pair, such as the coherence, to make a best guess estimate of what the deformation pattern should look like once all of these disconnected components are stacked on top of each other and we attempt to get a continuous deformation field. And so, for example, for this wrapped phase measurement, here is the corresponding unwrapped phase measurement. So now we can see that if we start from here, the deformation in this area steadily increases until we get to the actual epicenter of where this earthquake happened. And the same from the other side as well. In general, most InSAR processors will do this for you, but if you're trying to do it on your own, I would really recommend the Snafu software. It's been well tested by the community and used in many different places. It does have a strange spelling though, so the spelling here is SNAPHU. All right, so that's kind of the end of the broad overview of what InSAR is and how it works. But luckily, as you can tell, this is a relatively complicated process. And luckily, a lot of effort has gone into creating ways for you to work with InSAR data without having to actually calculate all these things on your own. And Alex demonstrated this a bit earlier with our Vertex search site, but I also wanted to show you another way you can do it if you're familiar with the Python programming language and Jupyter Notebooks inside of OpenSAR Lab. You can we have a service where you can request the generation of InSAR pairs directly from our services through Python. And the nice thing about that is that it makes it easier to generate request the number of interferograms that you typically need for large time series analyses. So it makes it much easier to request request 200, 300, 500 InSAR pairs at a time. So with that, I think I'm going to go ahead and switch over to Science Lab. I'm going to stop sharing for a second while I get over there. Okay. Alex, do you want to let me know when the Zoom level is good for everybody to see my Open Science Lab instance or OpenSAR Lab
Yes,
instance?
I can see it, and I think you've got a good Zoom level there.
Okay. So in order to start with our tutorials, there's a couple of things you'll need to do right off the bat, and this is something that Alex will be helping you guys with over the next couple of days. So the first is we need to create a Python environment that we can actually do to use all of our processing. So in the main level of OpenSAR Lab, first when you log in, there's this folder called Content Environments. And inside of this folder, which you can access by double clicking, you can actually go into this notebook called Install Content Environments in OpenSAR Lab using environment.yamls. So what you'll need to do here is just run the first couple cells of this notebook. You can run cells of a notebook by using the keyboard command Shift Enter, or by right clicking, or I'm not sure if you can do that by right clicking, but I typically use, what is the command? For just running one cell at a time, just by hitting
It's Shift Enter.
Shift Enter value. So like this.
Yep.
And so here you'll get, you'll just run these first few cells, you'll get a listing of what environments you do have currently installed. And then you'll want to get down to this cell right here that says select and a content environment to create. And you'll want to go down to these radio buttons and click the InSAR analysis option. And then once you have that one selected, keep running this notebook. And then eventually you'll be running these two cells here. I already have my environment set up. So for the sake of time, I won't be running these cells today, but go ahead, follow the prompts, and make sure to run this final cell as well. And that will get you all set up for the environment you need. Once you've done that, you'll need to go ahead and click this bright blue plus button in the upper left-hand corner and click on a terminal instance. And this will give you a command line where you can enter in a few commands that will allow us to grab the data for the tutorials that we're going to run. So this is just normal terminal, so you can run commands like ls, which will list off the files in this directory. But what we'll need to do, and I'll put this command in chat, is we'll need to copy in a specific GitHub repository that has the code we're going to be working with. So this code is housed under the webpage github.com/asfhype/tutorials. And don't worry, I'll post a link to this in chat, but you'll need to go in under this green code button right here and click under clone, the HTTPS option, and just click this little button to copy the website address. And then, I already have a version of this folder here. So I'll just go ahead and delete it. This won't be, you guys won't need to do that stuff, but here in this command line, you'll just need to type git clone and then paste in that website address. And that will go ahead and clone or copy in the notebook that we'll be working on today. And I'll go ahead and paste this into chat right now so you all have it. All right, there you go. Okay, and once we have that, we can go into this new folder that was created called tutorials. Under the NEAG 2023 folder, we can look at this HyP, SDK, InSAR. And so now we have this open, and this will be the notebook we're running today. So the first thing to do is make sure that we have the correct kernel set up. When you first start up, it'll be the base environment, but with the new content environment that we just installed with the first notebook, you can then go in and select InSAR analysis. And now we should be ready to go. So this gives a little bit of context in what we're going to be doing here, but basically we are going to be using two Python packages to actually request the processing of interferograms for an area we're interested in. The first package we're going to be using is a package called ASF_search, which allows us to basically interact with the Vertex search tools that Alex showed earlier, but inside of Python. And the next tool we're going to be using is the HyP SDK, which stands for the HyP Software Development Kit. And this basically allows you to request the generation of interferograms directly through Python. So this first cell just gives you a little bit of detail in what we're going to be doing here. Feel free to read this on your own time, but in particular, I'd really recommend you check out this InSAR on-demand story map. This is a great tutorial on InSAR that Heidi put together, and it really walks you through some of the basics that we talked about here and how the search goes. You know, if you were a little bit fuzzy on any parts of Alex's lecture, it'll walk you through the whole process so you can see how to do it via Vertex. It's a really great resource, and I use it myself a lot. So going back to our main notebook, we can use Shift-Enter to just run these first few cells. And the first thing we'll do is just import these two packages that we're going to be using, which you can just do with Shift-Enter. And the next thing we'll need to do is set up an instance of HyP for us to work with. So the way to do this is using, skip this cell for now, but then using the cell below it. You'll run this and it will prompt you for your NASA Earth Data login username and password. And this should be something that you have set up ahead of time. And I believe Alex had sent out instructions for how to do this, but I'm sure he'd be happy to help anybody who hasn't had it set up yet get this set up real quick. And so just in these boxes, you would type in your user ID and your password. You know, I'm not going to enter my password here in front of you guys while I'm sharing my screen. So this is an alternative way that I use to just set up a connection to HyP without showing my username here on the screen. But now that we have our connection to HyP set up, we'll then start actually using HyP to submit some InSAR jobs. And so the first thing to know is that HyP does more than just process InSAR. We have another several other types of jobs we offer. We offer RTC, or radiometric terrain corrected jobs. Excuse me. We offer autorift jobs that can be used to track the motion of glaciers. And then we're working on some new job types, specifically burst-based InSAR, which is going to be a really nice addition to our offerings. That'll be really great for anybody doing time series analyses or anybody who's working on InSAR for areas where they need high resolution but small spatial extents. So if you want to look at all supported job types and learn more about them, you can click on this link. But for this work, the first thing that we're going to do is use a few functions to actually create a nearest neighbor set of InSAR jobs that we can then use for completing a small baseline subset time series analysis, or SBAS for short. And so the first thing we're going to do is define a small function that will get us the nearest neighbors for a particular SAR image. And what this means is basically for a given SAR granule name that I specify here, give me the companion SAR images that are in the same location and orbit direction that occurred closest in time. So basically give us the ones with the smallest temporal baselines, which in general should have the highest coherence. So we'll define this function here. And then we'll go ahead and define the jobs we actually want to process. So here are the granules that or the SAR images for Sentinel-1 that we want to use to kind of demo this analysis. And in this particular case, we're using some SAR imagery over the Malaspina Glacier in Alaska. If you've never looked at the Malaspina Glacier before, it's really beautiful. It's kind of cool to look at inside light imagery. But this would be a place that you could sub in your own SAR imagery. So what we'll do here is we'll define granules that we want to be our reference granules. Typically, you would use a list of about, for a full analysis, you'd probably have a list of about 100 granules or so that you would be using as references, and that would get you data from Sentinel-1 all the way from 2015 to current day here in 2023. And then the next thing we want to do once we have the granules we want to create InSAR pairs defined is we want to create a project name. And so this is one thing to note here is this is a technique I'll often use when I'm doing a lot of bulk InSAR processing to make sure that I never create duplicate project names. So, what often happens is you might run this cell of the notebook, and if you just have a simple project name listed such as InSAR example, when you go to submit your jobs, it's very easy to accidentally run this cell again, and all of a sudden you have a duplicate of every job under the same project name, which it makes it really hard to make sure that you're only grabbing the data you want. And so what I do to kind of avoid this issue is that I add basically a small string of random letters and numbers to the end of the project name every time I run the cell, so that I always get a slightly different project name. And just to show you what this looks like, I can just divide this cell into two pieces right here and run it to just generate new project names. So you can see in this case, on the first run, it just creates the name of InSAR example RILM. And then if you run it again, this suffix at the end of the project name is changing. And this is just a nice best practice to make sure that you're always having distinct project names, no matter how many times you run this notebook. So we can go that for now and remerge these cells. So once we've set up the reference granules we want to use to find a project name for ourselves, we can then go ahead and actually request the generation of our jobs. So the first thing we'll do is we'll create a little container for all of our jobs to eventually go into. And then we'll use the, for each reference granule in our list, identified here by this for loop, we'll go ahead and get its nearest neighbors with a max of 2. So basically we're getting the 2 closest neighbors in times for each of these reference granules using the function that we defined right up here that I discussed a little bit earlier. And so once we have our reference scene and the neighbors that we want to use, we then can actually submit our InSAR jobs using this function, which is the HyP.submit InSAR job. And for this, we specify our reference granule name, our second granule name, or our secondary granule name, the project name that we defined up here, and then a couple of auxiliary options for what type of data we want back from this cell. So I'll go ahead and run this cell, and then I'll I'll talk a little bit more about the options that I've set here for the HyP submit InSAR job function. So, okay, those are off and running. We can follow the progress here on the progress bar that pops up. But the important thing to remember about this function is that it takes a couple of really important arguments. First is the granule names, granule 1 and granule 2. You won't be able to submit InSAR jobs without including that. The name argument will allow you to specify a project name that you can use to look up your jobs later. And then there are a series of many different arguments that you can specify that all start with include underscore something, something, something. And these are all arguments that you can use to specify that you want specific data products output with your InSAR image that you're using. And in particular, there are two really important ones that we want to include because they're required by MintPy, our time series software. And these are include look vectors and include DEM. Now, in general, there are many types of parameters you can use during InSAR analyses, but to make it as simple as possible, for actual processing parameters, we've limited it to just two that we allow you to modify when submitting HyP InSAR jobs. And that in particular is the number of looks. And this controls how much multi-looking or basically spatial averaging that you're doing to the SAR imagery before actually creating your InSAR images. And the important thing to know about this is it controls your output resolution. So if you're looking at higher resolutions, you want to set this to a lower number of looks. Right now we allow a 20x4 look and a 10x2 look. A 20x4 look will result in 80 meter pixel sizes in the output imagery, and 10x2 looks will get you 40 meter resolution. Now, it might seem that, well, I should always just pick the higher resolution because that's, it's always great to work with high resolution data. Excuse me, this isn't always necessarily the case for InSAR. The more multi-looks you take, or if you use 20x4 instead of 10x2, you're generally going to get higher coherence and higher quality InSAR measurements. So if you're not looking at very, very small deformation features, say if you're looking at earthquakes or even volcanic signatures, it's often better to use a higher number of looks just so that you can get a little bit more data quality with sacrificing a bit of resolution. And the second option is whether or not to apply a water mask. And in general, we typically recommend that you apply a water mask whenever possible. We found that in the unwrapping step, having water included in your scene can typically lead to a ton of errors that make it difficult to do time series analyses down the road. And so it's often beneficial to apply a water mask during processing. Now, a reason why you may not want to do this is if you're working in coastal areas or are trying to find deformation right at the coastline. And this is because our current water mask isn't optimized for everywhere in the world. So there might be areas where it actually clips off a part of the land that you're interested in. So typically what I recommend is run a few scenes with the water mask applied, go into your area of interest and see, okay, are the areas I actually want to look at viewable when we have the water mask applied? And if they are, go ahead and do everything with the water mask applied. But if that's not possible, go ahead and set the apply water mask to false. And if you want to learn more about, our thoughts on water masking and when to apply and when to not, this is another great story map created by Heidi that goes into some of these details about when and where you might want to use the water mask and what errors can start to propagate if you don't apply a water mask. So we've gone ahead and submitted our InSAR jobs, and what will this function, this HyP SDK library also gives us the ability to kind of monitor our jobs as they process. And the way you do that is quickly uncomment on this line here by just deleting this hashtag in front of it and then running this up. And what will happen here is basically you'll get a progress bar that shows up and just tells you how many of your jobs are complete. And then when this is all done, you will know that all your jobs are ready for download. An important thing to know is in these notebooks, this will kind of keep running for until all of your jobs are complete. So if you want to explore running some other cells, you'll have to go in here and press this square, which stops the processing of this cell. And you can just clear that output message and wait for this to process. And so what we then, once you've used this function to determine that, yep, all your jobs are ready, you can go down and use this cell to make sure that all your jobs have run. But in this case, they haven't run yet. But when they do, you can use these cells to determine, okay, how many of your jobs succeeded and got you the data you needed, and how many failed. And if you have any failed, just go ahead and resubmit them. They should probably work on the next pass. And then once you're done with all that, you can use this succeeded jobs object. You can go ahead and call the download files object, and this will go ahead and download your InSAR products to the local directory where you can use them for further processing. And this will be the input to the MinPy time series analyses that we do later on this week.